Welcome everyone. Today we are looking at how developers teach computers to understand human language, tracing the journey from classic coding shortcuts to modern AI. On the left side of the diagram, you see traditional machine learning. In this older approach, humans have to do the heavy lifting. We manually break text down into math features like counting how often words appear. Then we feed these numbers into classic math formulas like naive-bayes or support vector machines to get an answer. On the right side, you see the deep learning evolution. The big shift here is that the computer handles the feature hunting for us. Instead of a human breaking down the text, raw text goes into the input layer. The network automatically translates the word into a digital map of meanings called an embedding space. Then the data travels through a web of hidden layers, including recurrent and transformer networks, which mimic how a human brain processes clues. These layers automatically figure out the context, grammar, and deeper meaning of the words. To summarize, traditional methods on the left require humans to extract the features. Deep learning on the right lets the neural network to discover the features on its own. Ultimately, both paths help us solve real-world problems like analyzing sentiments, translating languages, or summarizing long text. Let's look at how we get started. We can break the entire field of machine learning down into three main categories: unsupervised, reinforcement, and supervised learning. Let's start with unsupervised learning. Think of this as giving a computer a massive pile of data with absolutely no labels, descriptions, or answers, and telling it to find a pattern. The computer uses algorithms like k-means to group similar items together based entirely on their hidden traits. Next is the reinforcement learning. This is a trial and error approach based on rewards. There are no answers or datasets here. Instead, an AI agent interacts with an environment, tries different actions, and gets a positive reward when it does something right or a penalty when it fails. Finally, we have a supervised learning, which is the core of our lecture today. This method relies on heavily labeled datasets. This means we give the computer both the questions and the correct answer upfront. Mathematically, we are mapping our independent variables, which are the clue or features in the data, to dependent variables, which are the final labels. By looking at thousands of these labeled examples, the model learns the exact mathematical boundary lines needed to accurately predict the answer for brand new unseen data. Before a model can execute any classification, we must address a fundamental reality. Mathematical models cannot read raw text. They require a digital numerical vectors, so data preprocessing is first necessary step. We execute this through these essential steps. First is NaN handling, where we look for missing data points using functions like isNull.any to prevent mathematical operation from failing during training. Second is label and one-hot encoding, which converts non-numeric text categories like sun or dinner into distinct binary columns so our equations don't imply an incorrect numerical rank. Third is standardization, where we apply min-max or z-score normalization. This scales all our numerical representations into a uniform range such as 0 to 1, ensuring that high magnitude variables don't completely dominate the model's weight updates. As shown in the code block, tools like scikit-learns label encoder handles this pipeline efficiently. Let's look at our two classic machine learning techniques for sorting text. On the left, we have a naive Bayes, which we can call the probabilist. Its logic is incredibly simple. It assumes every single word in a sentence is completely independent of the others. To make a prediction, it just calculates the probability of each word appearing in a specific category and multiplies them all together. Even though words in real life depend on context, this quick math makes naive Bayes a super fast and effective baseline. On the right hand side, there is sport vector machine or the geometrician. Instead of just counting frequencies, it plots data points as coordinates in a multi-dimensional space. Its goal is to draw a clean boundary line called hyperplane to separate the classes. You see the formula w dot x plus b is equal to 0 on the slide. This is just the high dimensional version of the classic line equation y is equal to mx plus c. You learned already in the algebra. The x represents our text data, the w represents the weights the model assigns to important words, and b is the bias that shifts our line. Setting it to a 0 gives us the exact boundary line that is at maximum possible distance from our closest data points, which we call sport vectors. While naive Bayes gives us a probabilistic guess, SVM physically draws a geometric border to divide our data. Now let's transition into deep learning by examining the biological shift, the anatomy of an artificial neuron. This architecture maps the mathematical equation of a simple line directly onto a physical processing node. Raw text features feed into the system as inputs denoted as x1, x2, x3. Each input is multiplied by a corresponding weight w, which act as a coefficient determining signal strength. These are pulled into a central node along with the bias b, creating a linear summation of w dot x plus b. The real magic happens at the next stage, the activation function. Without an activation function, a neural network is just a giant linear regression model, incapable of handling complex data. By passing the sum through nonlinear functions like sigmoid, tanh, or the industry standard ReLU, we introduce the mathematical nonlinearity required to draw highly complex curving decision boundaries. Let's look at how a neural network actually learns by breaking it down into a three-step loop. First, we have a phase 1 forward propagation. This is where input values flow from the left to right through the network. The data enters the input layer, travels through the hidden layers where it gets multiplied by weights, and triggers our activation functions. At the very end, it exits the output layer to give us a final predicted output, which we read as y prime. Think of y prime as the model's ultimate guess based on the clues it processed. Next is the phase 2, the loss function. We represent this with the capital J. The loss function acts like a digital ruler measuring the exact error or distance between the model's guess y prime and the absolute truth. If the loss is high, the model's guess was way off. Finally, we have phase 3, back propagation. The error signal travels backward through the network from right to left. The network calculates exactly which weights caused the mistake and updates them using the formula you see at the bottom. It subtracts a portion of the error from the old weights to create a new, smarter weights. The speed of this update is controlled by alpha, which is our learning rate. The model repeats this loop over and over until its guesses are incredibly accurate. As we build deeper networks, we run into a major roadblock: overfitting. This dilemma occurs when a model performs flawlessly on our training data but fails completely on unseen real world text. The network has not actually learned the semantic pattern of language, it has simply memorized the specific noise of the training input. To solve this, we implement a regularization technique called dropout. The mechanism is intentionally disruptive. During every single training epoch, we randomly and temporarily disable a set percentage of neurons, frequently around 30%, as visualized by the grayed out nodes on the slide. This forces the network to distribute its learned representations across all available paths, preventing it from overlying on any single memorized shortcut. The final result is highly resilient, generalized model that performed robustly out in the wild. Let's synthesize everything we have discussed by translating this architectural theory into production-ready Python code using Keras. We instantiate a sequential model and construct our architecture by adding a fully connected dense layer with 512 nodes. We inject nonlinearity immediately by applying the ReLU activation function, allowing our network to map complex boundaries. Next, we implement our regularization layer, dropout 0.3, which randomly spheres 30% of the active nodes during training to prevent the overfitting issue we just discussed. We then point our output layer to a dense 6 configuration with the softmax activation, creating normalized probability distributions for a 6-class classification problem. Finally, we define our training mechanics. In the compile step, we use categorical cross entropy as our loss function to measure prediction error and deploy the Adam optimizer to dynamically manage our learning rate during the back propagation. With just a few lines of code, the entire theory comes to life.